So here we're starting with our equation. Let's say we know how much mass the object has, what the temperature range is, and we know the specific heat capacity. Well, in that case, it's great for us because all we have to do is plug those variables in, plug those numbers in, and we can find the heat in joules, the heat energy in joules. But let's say we don't know the mass, but we do know how much the temperature changes. We know the specific heat capacity of the object. We know what material it's made out of, and we know how much heat energy it gave off. But we still need to know how much there was. All right, so we'll have to get mass by itself. Whenever we're trying to solve to get something by itself, we have to first look at getting it in the numerator. Then we have to look to get it alone, okay? So first, let's look to get it in the numerator. Well, it turns out that our mass is already in the numerator because we don't see a division sign above it, right? That would be being in the denominator, but there's no division sign above it. It is in the numerator, all right? So we don't have to move M anywhere because M is where it's supposed to be. However, M is not alone. It's hanging out with his friends. So all of M's friends need to go home. So we've got to get all of these off of the same side. Now, if we look at the relationship between M and delta T, it is multiplication because M is, there's no operation between the two. So we can assume that it is multiplication. Now let's look at the relationship between M and the specific heat capacity. It turns out that M is also being multiplied by the specific heat capacity. We don't have to multiply in any order. So M is being multiplied by delta T and it's being multiplied by the specific heat capacity. So the opposite operation will separate all of these things. So instead of multiplying, we're going to divide, and we're going to do that on both sides. Now, whatever I put in the denominator, I'll be able to cancel it out. So if I put delta T in the denominator, that means I can cancel out the delta T's. If I put the specific heat capacity in the denominator, I can cancel out both of the C's. All right, so let me do that on this side as well, delta T and CP. And that allows me to cancel those out because delta T divided by delta T equals 1, and CP divided by CP also equals 1. So I end up with heat is equal to delta T times Cp, which equals mass times 1 times 1. And anything times 1 it doesn't change. And so mass is equal to heat divided by delta T times the specific heat capacity. All right. Now let's do this process again, but let's solve for delta T. Okay. So let's say we know what the heat change is. We know how much energy was put into the object. We know the mass of the object, and we know the material the object was made of for the specific heat capacity. But we don't know how much the object changed temperature. All right. Well, to find that out, all we have to do is get delta T by itself. So first of all, delta T is in the numerator. So delta T is where it's supposed to be, so we don't need to move delta T. But delta T is not alone. So we need to, get delta T. It's time for its friends to go back home. So it has to be alone. So delta T is also being multiplied by M, and delta T is being multiplied by the specific heat capacity because there's no operation between them. So we know it's multiplication. So again, we're going to divide and do the opposite. And we can divide by anything up here, and that'll cause it to cancel out. All right. So our M's cancel out and equal 1. And our CP's also cancel out and equal 1 because we have CP up top, CP in the bottom, that equals 1. M up top, M in the bottom, that equals 1. So now we have heat over mass times the specific heat capacity is equal to the change in temperature. So now we know the amount of change in temperature of the object. So that's great. Now let's do one more just to make sure we understand what's going on. All right. So now let's say we know the amount of energy that it took to heat up the object. We know the mass of the object, and we know how much it changed temperature. But we're trying to figure out, okay, so what is the material? What material is the object made out of? Well, we can find that. We can find the specific heat capacity of the object's of the material by getting Cp by itself. Okay, so similar situation. Cp is already in the numerator, so it is where it's supposed to be, so we don't need to mess with it. However, it's hanging out with its friends, and it is not alone. So it is time for its friends to go back home. So we need to move mass and delta T back to their house. All right. So currently, again, the specific heat capacity is being multiplied by mass and delta T because we don't see any operation between them. So we assume it's multiplication. So we can actually divide by both sides to undo this. And we'll divide by mass times delta T. All right. And M over M will give us 1. And delta T divided by delta T is going to equal 1. Okay. So we end up with Q over mass times delta T, which equals 1 times the specific heat capacity. And anything times 1 is unchanged. So the specific heat capacity is equal to the heat energy divided by the mass times the change in temperature. All right. So hopefully this was helpful in explaining to you all the heat equation. It is a very cool equation as it begins to get you into material science, which is a very cool area of physics where you study the materials that are used to make objects, and you can actually choose which materials to use. And that's how you get things like breathable shirts that are better for exercising in because they keep you cool, and as opposed to the cotton. So hope you all have a great day, and thanks for tuning in.